Okay, so in this question we have a circuit with a switch, and we're being asked to evaluate and prove various statements about brightness of bulbs as we change things in the circuit. And so this is a pretty long question, and so there are also multiple different ways you can kind of approach any of the various solutions. So I'm not going to do every possible way, but I'm probably going to mention a couple of them kind of as I go. So if you get the same answer with what you think is the same process or a similar process, but a slightly different one, you probably are still right. Okay, so we have our circuit. I'm just going to draw the light bulbs as circles to save some time. And our switch, and our battery, right? And we're told that the battery has EMF epsilon, and all the light bulbs are identical. So we aren't told what the resistance is, but we know they're all identical. So I'm just going to call it R, right? Just for simplicity. Once they're identical, we know they're all the same. That's the key. So now we're ready to actually look at the problem. So part A, we have a prediction. Bulb 1 will get dimmer, or will decrease in brightness when the switch is closed. The first part is, do we agree or disagree? And to do that, we need to look at sort of what changes about the circuit as a whole. If we close the switch, we give the current, instead of just one path, two paths. So that's going to lower the equivalent resistance, right? So by giving the current a second path, we have to lower the equivalent resistance. You can calculate it exactly, but since this is a qualitative explanation of the reasoning, we don't need that number or that equation yet. All we know is that because if we gave it more paths, we have to lower the equivalent resistance. Then, because the battery remains constant and our resistance goes down, we can therefore conclude the current coming out of the battery must go up, right? That's from Ohm's law. And since the current from the battery and the current through light bulb 1, I should give these all numbers, right? This is 1, 2, and 3. So the current from the battery and through bulb 1 are the same, because they are in series, right? There's no junctions. So now we know that the current through battery 1 must go up. And so the final statement is that we know that the power relates to current with I squared R. And power is the same idea as brightness. So all these statements lead us to conclude that the brightness must go up. So we would say, I disagree with the student, kind of outline some of this reasoning. So A part 2, we need to actually do the math. So we want to show exactly how much the power changes. And the easiest way I think to do this is to sort of describe the power before and the power after, and then put the two pieces together. Even though that means we're going to be writing like P1 in terms of things that we aren't allowed our final answer to be in, and P new in terms of things we aren't allowed the final answer to be in. That's the simplest way. So we're going to do like the switch open. All right, so switch open first. With the switch open, because it's just two bulbs that are identical in series, we know that delta V1 is half the EMF of the battery, right? And we know that power, another way of writing that, is this, right? So this is epsilon squared over 4R, right? Okay, good. With the switch closed, we have to do a little bit more work because the circuit's a bit more complicated, right? So the equivalent resistance changes. It used to be 2R. Now it's R in series with two in parallel, which is r plus r over 2, or 3r over 2, right? As you can see, it has indeed gone down. 3r over 2 is less than 2r. And so this tells us now I battery, right? I battery is delta V over R, but the battery's EMF is epsilon. So that's 2 epsilon over 3R, right? And we know that the current that comes out of the battery is still the same as the current going through bulb 1. And we also have another expression for power, I squared R, right? So 4 epsilon squared over 9 R squared times R, or 4 epsilon squared over 9 R. This is P nu, right? So now we have something close. I'm going to take this expression, and I'm going to rearrange it. I'm going to get epsilon squared over R is 4 P1. And I'm going to take this and put that in right there. So now we'll get one expression that combines P nu in terms of P1, and that will be, right, this, P nu equals 4 ninths times 4 P1, or 16 P1 over 9, right? And so there's multiple different ways you can arrive at this depending on whether you calculate potential differences or currents or vice versa. I think this is about the simplest, but however you approach it, this is kind of the process. Okay. And so part 3 I'm not actually going to write because we've kind of already done it. So how does the result of the derivation in part 2 relate to the explanation in A part 1? Well, in A part 1, we go back here, right? We said Req goes down, therefore the current goes up, and therefore, since the current and the power go together, the power must go up. Therefore, the bulb's brighter. And right in here, right, here we calculated Req goes down, and here we calculated the power goes up. And since we showed that the power goes up, that's the justification that the bulb cannot get dimmer, right? So that's kind of the process there. Right, so concluding that 16 ninths is greater than 1, basically. Okay, so that's the whole of part A, which was 7 of the 12 points, so the biggest part of the problem. So part B, we have a prediction about bulb 2. So we were saying that bulb 2 is going to decrease in brightness. I'm going to redraw the circuit here. Bulb 2 is going to decrease in brightness if we close this switch. That's the statement that's made. So 1, 2, that's kind of a bad 3. 3, okay. So we close the switch. Now, before, we needed the total current going through here, and after, we'll only get a little bit and a little bit going that way. So because of the junction rule, once we create that another junction, we know that I open must be less than I closed, right? The junction rule tells us that. Because as long as some current goes through there, then it must be some smaller amount. Although, as I said, that is actually a little bit of an incomplete explanation because we can potentially have more total current coming from the battery to make this not true. So I think we need to be a bit more formal, even in words. Although the point was awarded for if you just said that the current must decrease, I'm not entirely convinced that that's an absolutely true statement depending on the relative resistances. But, well, actually, no. Since the bulbs are identical, this is an absolutely true statement. If they weren't identical, you'd have to do a little bit more work to verify that statement. Yeah, but this is good. So since we've concluded that the current must go down, I wrote this backwards. Right, I wrote that backwards. I open has to be greater than I close. So the current goes down when we close the switch. And since P I squared R, if this goes down, then the power must also go down. And so therefore the student is right, bulb 2 will decrease in brightness. So justify your explanation with the calculation. So here's where we need to actually do the math. since I've chosen current for my explanation, I need to show that the current must go down. So when the switch is open, we know I is I battery because it's all just one series circuit. And if we see what we calculated. Actually, we didn't calculate that before. That pretty quickly because we have the total potential difference over the total resistance, the equivalent resistance of the circuit, just two resistors in series. When it's closed, we know I battery becomes 2 epsilon over 3R. Let me go back and check that. Yeah, that's this line right. So we know what the current coming out of the battery is, then we just need to figure out the junction part. And again, this is actually pretty easy because they're identical resistors. Since they're identical resistors, the current has to split evenly. So we conclude that I2 equals I battery over 2. So equals 1, actually I'm not going to write the 1. So epsilon over 3R. Right, and so this and this we can compare, and we see that the current does indeed go down, so that supports our statement. All right, finally, part C. Now we're replacing things with a capacitor. So the switch is open, we replace bulb 3 with a capacitor, and we close it. So this is all just writing, so I'm not going to, actually I'll go back. Picture of the circuit rather than new. All right, so this is what our circuit looks like. We are going to replace that, and we're going to close the switch. So I'm just going to draw in a capacitor and then the switch closed. So immediately after the switch is closed, this behaves, right, as if it's just a wire. It's as if it's not a gap at all. So it's essentially a short circuit. All the current will go around and skip bulb 2 entirely. So bulb 1, since it still has to get the current from the battery, bulb 1 will be brighter than bulb 2 because bulb 2 is out and bulb 1 is on, right? Because the capacitor behaves essentially just like a wire. In the second part, after a long time, the capacitor is essentially fully charged and no more charge can flow in that path at all. So that's as if it's a broken circuit. After a long time. And so since no charge flows there at all of it has to go through that path. And so this is just as if the switch was open. We've already discussed that since they're identical resistors in series with the same battery, they must be the same brightness. Okay? And so there's lots of writing to do here, but if you're careful with sort of your circuit analysis and the use of the junction law, Ohm's law, and the loop law, you can sort of put it into words, basically just as I've talked about.